Hello and welcome to Unit 6, Day 2. This is Algebra Honors Unit 6 on exponents and radicals. This is our second day. Yesterday we talked about what happens with an exponent when the exponent is 0 or negative. Today we're going to talk about what happens when you multiply monomials that have exponents. So we've used the word term already. A term is just a single number or variable, or numbers and variables multiplied together so that you have something that is a coefficient and a variable. So terms are things that are separated by adding or subtracting or equals. So when we're looking at terms, I might have 3x plus 5y minus 7 equals 2m plus, 3. Okay, so anything that's separated by plus or minus is a term. So we have a term 3x. This term is actually 5y, positive 5y. This term is negative 7. We are combining those things. There's 3 terms on the left side of the equal sign. 2m is a term, and positive 3 is a term. So terms are just things that are being separated by adding or subtracting. And when we say a single number, negative 7 is a single number, positive 3 is a single number. 3x, that really means 3 times x. So that's what we're saying if they are things that are multiplied together. So a monomial is any one of these terms all by itself. 3x, that's a monomial. 5y cubed, that's a monomial, right? Just the one thing. Okay, so we know how to add and subtract monomials. We call that combining like terms, right? So you look at the coefficients and you combine those coefficients. You're adding numbers or subtracting numbers. You are only allowed to combine like terms if they are in fact like terms. And so that means that they have exactly the same variable that has exactly the same exponent. All right. Today we're going to figure out what we do when we need to multiply monomials together. Okay. Just a reminder, sorry, any time you have an exponent of 0, a to the 0, it doesn't matter what a is, it equals 1, okay? And we assume that a is not 0. Negative exponents, if we have a non-zero number a and an integer exponent n, if I have a to the negative n, I can rewrite that with a positive exponent by changing the location. So a to the negative n becomes 1 over a to the positive n. Or if I start out with 1 over a to the negative n here, I'm going to relocate a to the negative n and put it in the numerator. And that's the numerator just because there is an invisible 1 in the denominator. Okay, so when a term does not have a visible exponent, you assume it's 1. Okay, it is understood to be 1. X really has a positive 1 exponent. If a term does not have a visible coefficient, there's no number before it. X here has a coefficient of 1. Okay, 1, 1. And if it's a negative of the variable, it's really a negative 1. Negative a really means it's negative 1 times a. All right, those are just some old-fashioned reminders that you have in your head somewhere. So we're going to start out product of powers. So we have 2 numbers, x to the m times x to the n. Our base is exactly the same, has to have the same base. If your base is the same, you solve this by adding the exponents. So I keep my base, my new exponent is m plus n. So if I had 3 squared times 3 to the 3rd, actual numbers that we can work with, you know this means 3 times 3 here, right? Times 3 times 3 times 3, yeah? That's 3 times 2, or sorry, 3 times 3, 3 times itself 2 times. That's 3 times itself 3 times. If I rewrite this, change it from expanded form to an exponent, my base is 3, and I have 1, 2, 3, 4, 5. I'm multiplying it by itself 5 times. That's what we are saying our rule means. We start with 3 squared times 3 to the 3rd. We notice that we have the same base, and we're going to add our exponents. and so we end up with 3 to the 5. And you can do the math, and you can confirm that if you want to using your calculator. Okay, why does it work? Well, 2 squared times 2 to the third really means 2 times 2 times 2 times 2 times 2, right? And so if I want to simplify that, I'm going to say that that is 2 to the 5th power. All right. 2 to the 5th power on the calculator, 2 times 2 times 2 times 2 times 2, so I do that 5 times, it equals 32, which is as simplified as I can get. I have h squared times h. Okay, in this case, I have a variable, so if I had coefficients, numbers that I could multiply, I would. But there's just a 1h squared times 1h, so 1 times 1 is still just 1. Okay, so I get to look at my h squared, that means really h times h, times h. H squared times h. H times h times h is really h to the third. There's no easier way to write that. 3a squared b cubed times 2a cubed. Well, in this case, I actually have numbers that I can multiply together, and I have variables. Okay, all of this is being multiplied together. So I'm going to do the math I can. I can multiply 3 times 2. 3 times 2. And then I have a squared, so that's a times a. And I have b cubed, so times b times b times b. And I have a cubed right here, a times a times a. So I've kind of broken this up. I pulled my numbers out to the front, and then I expanded out. A squared is a times a, b cubed is b times b times b, and then over here a cubed I still have to deal with is a times a times a. 3 times 2 is 6. A times a times a times a times a is really a to the 5th. And b times b times b is really b to the 3rd. Okay, you know that if you're looking at a squared times a to the 3rd, a squared times a to the 3rd, you can solve that by saying a to the 2 plus 3, which we call a to the 5th. Okay, so that's just a little part of our problem. A squared times a to the 3rd was a to the 5th. But if I expand it all out, and then smush it all back together again, I'm going to get 6a to the 5th, b to the 3rd. Okay, there are several different ways to look at that, so you can take a look at the printed key and see if that helps you in any better way. All right, we're going to practice. We're going to practice here. Remember, if we have the same base and we are multiplying a bunch of the same bases together, we get to add the exponents. I have 2 times an invisible 1 coefficient times an invisible 1 coefficient. So 2 is the number that stays as the coefficient. I have x to the 3rd times x to the 4th times x squared. So I'm going to keep my base, x, and I'm going to add those exponents together. Okay, so this really equals 2 times x to the 9th. Over here, I have 2 times y to the negative 3 times 3 times y to the 6. So I know you already have some ideas on what you could do with that negative 3, but I'm going to say hold off. We're not going to put that in the denominator just yet. Right now, I have 2 times 3 that I can do, 2 times 3. And then I have times y to the negative 3 times y to the 6. Let's do this methodically. 2 times 3 I know is 6 times y to the negative 3 times y to the 6. Well, we've said our rule is that we get to keep the base, so 6 times my base, y, and I'm going to add those exponents, negative 3 plus 6. When I do that, I get 6y, negative 3 plus 6 is 3, right? That is my answer, 6y to the 3rd. Sorry, I'm looking at the old key that I am looking at, and we actually made a mistake on the old key. So this, I believe, is the correct answer. All right, Let's look over here and see what we can do. I'm going to multiply my numbers together. -7 times -4 is 28. Then I have p's, p to the 9th and p squared. So that's going to be p to the 9 plus 2. Okay, I'm going to take care of the q's. So I have q to the 3 plus 6. And then I'm just, I have r's. R to the invisible 1. Don't lose that 1. There is an r here. Okay, so it's going to be r to the 1 plus 4. This is really r to the 1. Don't lose that exponent, okay? All right, simplify. 28p to the 11, q to the 9, r to the 5. Okay, we made it through our first page of notes. And so, take a quick breather, because now we are making things a little bit different. This time, it's the power of a power, okay? Before, we said the product of a power. Product of a power. Notice the difference. A product is when you multiply two things together, or more, right? And powers are exponents, sort of, mostly. Okay, so power of a power, I'm going to have something that's raised to a power, and I'm going to raise it to a different power, or maybe the same power. All right, so what we do for this is it's power of a power. I'm going to keep my base, and I'm going to multiply m times n. And that's going to be my new expression. And of course, it's even neater to write that as x to the mn. We don't need the multiplication sign because it's implied. All right, so let's look at some examples and see if we can make sure we are proving this to ourselves. 2 to the 3rd times 2. If I follow my rule, then I am saying that this is 2 to the 3 times 2, right? Which equals 2 to the 6th. So let's see. 2 cubed squared means 2 cubed times 2 cubed, right? Well, if we go back to the rule we just used, that means we keep our base 2, and that's 3 plus 3, so that's 2 to the 6th. Or I can look at it this way, 2 times 2 times 2, that's 2 cubed, times 2 times 2 times 2, also 2 to the 6th. So now we have even more ways to prove ourselves here, right? 2 to the 6th, if I multiply 2 times 2, 4 times 2 is 8, 16, 32, 64. 2 to the 6th equals 64. So all the way simplified, we get 64. Okay, and again, if you put this in your calculator, you put the number 2, you press the y to the x button, and then you tell it the exponent you want is 6, and then you say equals. All right, here, if I'm following my rules, this means x to the 2 times 4, which means x to the 8. Okay, if I expand it out, it's really x squared times x squared times x squared times x squared. Now I'm multiplying a bunch of things with the same base, so I can add my exponents. So 2 plus 2 is 4, plus 2 is 6, plus 2 is 8. Or I can think of it as x times 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 x. That again, when I put them all together, I have 1, 2, 3, 4, 5, 6, 7, 8. I have x multiplied by itself 8 times. Since we don't know what x is, we can't write anything any simpler than that. It's just x to the 8. Okay. And so I'm going to just follow my rules here. Now that I've proven it to myself, I'm going to trust the rules. So I'm going to say that that is x to the 3 times 6, which is x to the 18. I'm going to say, whoa, I got negatives, and I've got lots of stuff going on. So GEMDAS still applies here. This means x to the negative 2 times x to the 5th raised to the 2nd power. And so I have to follow GEMDAS. I have to do this part first. I have to do the exponent first. So I'm just going to keep x to the negative 2, and I'm going to say that's times x to the 5 times 2, right? That's what that means. I have x to the negative 2 times x to the 10. Now I'm back to product of a power rule. And so I keep my base, and I add -2 and 10, so I get x to the 8 as my answer. Okay. Again, we have a whole lot of stuff going on. So order of operations tells me that I have to do this part first because this part has an exponent on top of an exponent, basically. Okay, so I'm going to bring down -3x squared, and now I have times y to the 2 times -3. So be neat when you're writing things here because you don't want to accidentally be adding and subtracting when you mean to be multiplying. -3x squared times y to the -6. -3x squared times y to the -6. I can't really simplify much, but I don't like to have a negative exponent. We know that, and so we're going to rewrite that and make it prettier. And we are going to relocate y to the -6. -3x squared stays in the numerator, and y to the 6th goes to the denominator, just so that I can have a positive exponent. Okay, oops, I don't know what I just did, hold on. Okay, I think I'm kind of back in the general size that I was doing. Sorry about that. All right, so back on page 1. Notice these words, product of powers. Okay, we had the product of a base that had a power. Then we had power of a power. So we had some base raised to a power that was all raised to a different power. Now we have power of a product. Power of a product. So we're going to have some product, two numbers multiplied together, and then raise it to a power. All right, so to find a power of a product, we can find the power of each factor in there and then multiply. Okay, what I mean to say is that this x times y, x is a factor and y is a factor. If I have the product raised to the power of m, I can actually break it up and I can find the power for each one of those factors. So this m is going to, the power of m is going to every factor inside. So this equals x to the m times y to the m. Okay, it was x times y all raised to the m. Now it's x to the m times y to the m. Which you can write as x to the m, y to the m if you want to. Okay, so let's see why it works. I have 3 times 2, all raised to the power of 2. So what I am telling you up here with this rule is that I can distribute that exponent to all the factors inside. So I'm telling you that this is going to be 3 squared times 2 squared. Okay? And I know then that that's 9 times 4, right? 3 squared times 2 squared is 9 times 4, which equals 36. So if we use my rules with an example like this, we can break it all out and we find out that our answer is 36. You also know that if you follow GEMDAS and you have 3 times 2 all to the power of 2, you can do order of operations. You can do the stuff inside the parentheses and you get 6. And then you're going to now do your exponents, right? And 6 squared is 36. And that's the answer we got, 36. So woohoo, we got the right answer, right? Either way, it's 36. So for something like this, you can choose which way you want to do it, whether you're using the order of operations or whether you're using these rules with our exponents. When you have variables, though, you are going to have to use the rules. Okay, so this next example, we have to use the rules. I have 3 times x inside those parentheses. It's all raised to the power of 2. So for every factor inside, I'm going to raise it to the power of 2, okay? So I'm now going to have 3 squared times x squared. Every factor inside got that exponent. So I know that that's 3 times x squared, so I know it's 9x squared. I can't simplify that at all. This will be just 9x squared. Okay, if you wanted to back up and think about this as being 3x squared, so it's 3x times 3x, oops, x. 3 times 3 is 9, and x times x is x squared. So there are several ways that you can get to our answer. No matter what you do, hopefully, you're going to get 9x squared. All right, now I have 3 factors inside my parentheses. I have 2 times a squared times b. This 3 has to go to every single factor. So this, where I've got a 2, that's going to be like your number 1 mistake, I bet. Or if I can't see an exponent, that's another place that I might forget to distribute that outer exponent. This is going to be 2 cubed times a squared cubed, so a to the 2 times 3, times b to the invisible 1 times 3. Okay, that is 8 times a to the 6 times b to the 3rd. I could also expand it out. I know that that's the same thing as saying 2a squared b 3 times, right? Because the exponent is 3 times 2a squared b times 2a squared b. When I do that, 2 times 2 times 2, 2 times 2 is 4, times 2 is 8. And then I have a squared times a squared times a squared. I got all the a's. And then I have b times b times b. I got all the b's. If I simplify that, I have 8. My base of a, if I have the same base, I can add those exponents. 2 plus 2 is 4, plus 2 is 6. I have the same base b, and I'm going to add those exponents. It's a 1, it's a 1, it's a 1. 1, 1, 1. I have total of 3 of those.